Hi everyone. So this is following up on lesson 2.1 where I did a second recording to show you it and all of the examples using the substitution method rather than my method that I showed you in the original videos for lesson 2.1 and 2.2. So in this video, I'm going to use the substitution method again, but for different types of derivatives. The first one we're going to talk about is exponential form. This was always the easiest derivative because if you had a function like e to the exponent u, the derivative was simply the same thing, e to the exponent u, multiplied by the derivative of that function that's in the exponent here, okay? So du by dx. The integral, okay, works the same way. So the integral of e to the u, du, is equal to that same function e to the u plus a constant. So again, the integral is also a very straightforward form when we talk about the exponential form, okay? So starting with a couple of examples, again, I will do these purely using the substitution method. We have evaluate the integral of x squared e to the 4x cubed dx. So what I notice here when you use substitution method is the easiest way is again to pick, in this case, what I call the more advanced function, e to the 4x cubed here, what I deem the more advanced function. Usually the function that's easier to take the derivative of, or in this case, the more advanced function, works well, right? So the e function, you saw taking the derivative of the integral is very straightforward. And that's helpful when we look at the substitution method. So I'm going to let u equal e to the 4x cubed. So du by dx is equal to e to the 4x cubed. In this case, times the derivative of this item here, which is 12x squared. Okay, so if I take, now I have to solve for du. So to do that, I can multiply both sides by dx, just like you saw in lesson 1.1. So the dx's here will cancel, and we're left with du is equal to, simplifying this, 12x squared e to the 4x cubed dx. Okay, well, we're almost there, right? This looks very similar, except we have the 12 here. So to remove that, we have to divide both sides by 12. And if we do, we end up with 1 over 12 du is equal to x squared e to the 4x cubed dx. So we can now substitute this in. This is actually the entire function. Okay, so what we're left with here is the integral of 1 over 12 du. Okay, so if I move the constant outside of the integral, we have 1 over 12 times the integral of du. And the integral of du is just u. Okay, just like when we had the integral of dx was equal to x, the same thing is the case here. So we have the integral of du is simply 1 over 12 times u plus, obviously at the end, a constant. Okay, very simple integral this way. And if you substitute in u, we get 1 over 12 e to the 4x cubed plus a constant. Okay, so slightly different than when I did it in lesson 2.2. Again, after hearing your feedback, I've noticed that this method seems to be easier for all of you to follow versus the way I did, which was more by both using part substitution, but also looking at it by inspection. So our second example, okay, moving away from e, we still have an e function, but we also have trigonometric. So it's the integral of 3 times cosine theta, e to the sine theta d theta. Again, you always try and pick the more advanced function or the easier one to differentiate as the function u, because you're always going to differentiate it and find du, right? Because you're trying to substitute that in. So I'm going to pick e to the exponent sine theta. Okay. So let u equal e to the sine theta. Anytime you see an e function, it's always good to select that. I mean, not only in this case is it the more advanced function, but it's really easy to differentiate. We saw that when you looked at the derivative of e to the x is just e to the x. Okay. So taking the derivative, we have du by dx is equal to e to the sine theta multiplied by the derivative of the exponent, which is cosine theta. In this case now, solving for du, I'm going to multiply both sides by dx. Dx is canceled here, and we're left with du is equal to e to the sine theta cosine theta dx. And you can see that's almost the whole function here except for this number 3, which again, a constant in an integral doesn't matter because you can move it out of the integral. So substituting this value in now, we get the integral of 3 times du. Now, moving the 3 out of the integral, we get 3 times the integral of du. And remember, the integral of du is simply u. So if we do that, we get 3 times u plus a constant. Okay? So if I substitute in, all right, the constant here, then we get 3 times e to the sine theta plus a constant. All right? So our third example here is not necessarily right off the start as intuitive as what you'd pick for u if you use substitution. And that's because there's 3 terms here. So it's evaluate the integral of 4 e to the 3x minus 3 e to the x divided by e to the x plus 1. So the first step you can do here is you can see here that there's 3 terms, all of which are powers with the base of e and an exponent. So you can actually use the laws of exponents to simplify this first before using the substitution method. Okay? So I'm going to write this as the integral of 4 e to the 3x divided by e to the x plus 1 minus the integral of 3 e to the x over e to the x plus 1. Okay? I didn't put the dx on each. Okay? And that's because since they're divided by the one term here, that's the same as each term individually divided by that term. So now, what I'm going to do next is remove the constants. Okay? So move them out of the integral. So we have 4 times the integral of e to the 3x over e to the x plus 1 minus 3 times the integral of e to the x over e to the x plus 1. So now we have just powers in the integral. And with the laws of exponents, if you have one power divided by another, and they have the same base, then you can subtract the exponents. So if I do a sign bar, I'll do it up here. For the first term, we have e to the 3x minus x plus 1. For the second term, we have e to the x minus x plus 1. Again, I just subtracted the exponents from in the denominator from the numerator. So if I simplify each of these, I'll get e to the 3x minus x minus 1, which is e to the 2x minus 1. And for the second term, I have e to the x minus 1, which is simply e to the minus 1, or 1 divided by e. And since it's just e to the exponent 1, that's actually a constant. Okay? So we can substitute these values back in instead of having the fractions that we had in each of them. That gives us 4 times the integral of e to the 2, oops, that's not a 2, 2x minus 1, minus 3 times the integral of 1 over e times dx. Okay, so the second integral here just becomes the integral of dx because it's just a constant. So the only one that we have to look at doing substitution is the first integral. Okay, So if we do that, on this first integral, I'll do it in blue. I'm going to let u equal e to the 2x minus 1. So du by dx is the same, I did it again, e to the 2x minus 1 times the derivative of the exponent, which is simply 2. So now, simplifying, solving for dx, I'll multiply both sides by dx, solving for du. And I get du is equal to 2e to the 2x minus 1 dx. Okay? And you can see I only have e to the 2x minus 1 times dx here. So I don't want that 2 on the right-hand side, so I'm going to divide both sides by 2. And we have 1/2 du is equal to e to the 2x minus 1 dx. So substituting that in, I get 4 times the integral of 1/2 du minus, in this case, I just have constants. This is just 3 over e times the integral of dx. Okay? So now taking these integrals, again, they're both simple integrals now. It's 4 times 1/2, and now the integral of du is just u, minus 3 over e times x. Okay? And then, of course, we have a constant. So simplifying, 4 times 1/2 is 2, and substituting our value for u in, what we're left with is 2 times e to the 2x minus 1 minus 3 over e times x plus a constant. Okay? Okay, so now I want to talk about trigonometric forms. We went over the derivatives in the last unit of all these different trigonometric forms. Sine, cosine, tangent, and their inverse functions, cotangent, cosecant, and secant. Now we're going to look at working backwards to find their integrals. Okay, so the derivative of sine of a function u is cosine times du by dx. The integral, therefore, would be the integral of cosine would yield sine. Okay, so it's functions like that where we know the integral. So these integrals are ones I would provide you on the formula sheet. I don't expect you to memorize integrals like this. What I do expect you to do is to apply them to given problems. We are going to see in the next example, as you see here, we have cosine of a function u. Okay, and for the substitution rule, we're always picking the function u. So when you look at these basic kind of trigonometric functions, you're going to see that the way we select u is a little bit different in order to use the substitution rule. Okay, so let's look at the first example that I have here. And it's the integral of 2x cubed cosine 3x to the exponent 4 dx. So I've always said take the more advanced function. In this case, it's mostly true, but instead of taking the entire function, we're only going to take the 3x to the exponent 4. Okay, so that is a more advanced function compared to the x cubed function. But remember, all the integrals we saw, so in this case, the integral of cosine was of a function u, okay, was equal to sine u. So for that reason, what we pick in our substitution rule is the function inside the trigonometric in this case. So I'm going to let u equal 3x to the exponent 4. So du by dx is equal to 12x cubed. So if we want to solve for du, we multiply both sides by dx. So the dx is here, cancel, and du is 12x cubed dx. Okay. So the item here, we have a 2 here. We can't substitute in that 12, right? Because we don't have it in the function. So like we've done in the past, we have to divide both sides by 12. So we have 1 over 12 du is equal to x cubed times dx. So now we're going to substitute these values in. So we're left with, I'm going to move the 2 outside of the integral. 2 times the integral of x cubed dx is now 1 over 12 du. But before that, we're left with cosine of the function u times now 1 over 12 du, replacing the x cubed and the dx with the 1 over 12 du. So again, moving that fraction outside of the integral, we get the integral of 2 over 12, okay, which reduces down to 1 over 6, times the integral of cosine u du. Now, using those tables that you saw in the previous slide, we know what this integral is, okay? The integral of that is 1 over 6 times sine of the function u plus a constant, okay? Always plus a constant. So now we can simply substitute in our value for u, and we get 1 over 6 sine of 3x to the exponent 4 plus a constant. Okay, so slightly different in how we approach letting u equal a function here when it's a trigonometric function. Example number 2, okay, we have evaluate the integral of 1 over 6 cosecant of 2x cotangent of 2x dx. Again, different in how we approach the function u. Okay, so we know from that table that the integral of cosecant of a function u, cotangent of a function u, is equal to just negative cosecant of that function u. We almost have that here, okay? Except our function here isn't just x or something, it's 2x. So we know that we must let u equal the function in each of these trigonometric functions, okay? So I'm going to let u equal 2x. So that means du is just, du by dx is just equal to 2. So solving for that, we get du is equal to 2 dx. Again, we don't have a 2 here. So to just substitute in for dx, we divide both sides by 2, and we get 1/2 du is equal to dx. So we have a function for u, and we have a dx. So substituting these in, we end up with the integral of 1 over 6 cosecant of a function u, cotangent of the function u, times 1/2 du. Okay, that's a bad du. du. So I'm going to move the constants outside of the integral once again. So we have 1 over 6 times 1 over 2 is 1 over 12, times the integral of cosecant u, cotangent u du. So it looks exactly the same as this. So now we can simply take the integral, and we're left with 1 over 12 times negative cosecant of the function u plus a constant. Substituting back in u, we get negative 1 over 12 cosecant of 2x plus a constant. Okay? So our last topic for this is, again, remember in the first lesson we did the power rule, and then we found out for certain functions you had to, instead of using the power rule in your final answer, it ended up being the ln of the function. The same thing happens in trigonometric functions. There are certain trigonometric functions that their integral is the ln of an associated function, not necessarily the same one. So I've listed 4 of them here. So the first one is the integral of tangent and the inverse, which is cotangent, and then secant and cosecant of a function u. So using the substitution method is the same in that we're going to use whatever is within the trigonometric functions as our value for u. But just know that instead we're going to have the ln of these functions as the integral, okay? So if it's tangent, it's the negative ln of cosine of u. Okay, if it's cotangent, it's the ln of sine of the function u. And then looking at the last two, for the integral of secant, it's the ln of secant plus tangent. And for cosecant, it's the ln of cosecant minus cotangent u. Okay, but all of them still involve the same function u. Okay, so that's kind of the consistent part between each of these. So we're only going to look at one example here. Okay, just an additional trigonometric example. So evaluate the integral of tan of 2 theta minus 3 d theta. In this case, you remember, for substitution rule, we use the function inside the trigonometric function. So I'm going to let u equal 2 theta minus 3. So du, in this case, by d theta, is equal to 2. So solving for du, by multiplying both sides by d theta, we get du, that's a terrible du is equal to 2 d theta. Again, we can't substitute in the 2 here because there isn't one in this expression. So I'm going to divide both sides by 2, and what we're left with is 1/2 du is equal to d theta. So substituting all these values in, we get the integral of tan of u times 1/2 du. So moving the constant outside of the integral, we get 1/2 of the integral of tan u du. Again, from our table in the last slide, you'll see that this is the same as the integral of tan u is simply the negative ln of the cosine of u. Again, remember, absolute value in all these cases because the ln function is undefined when the value is less than 0 or equal to 0. Okay, so we can use that to find the corresponding integral, and we're left with 1/2 times the negative ln of cosine of u, the absolute value, plus a constant. So our last step here is simply to substitute in the value of u. So we get negative 1/2 ln of, in this case, cosine 2 theta minus 3 plus a constant. Okay? So that was it for this lesson. Again, all of this comes down to practice. Figuring out when to or what to use for you in the substitution rule can either make these questions really easy for you, or they can make them horrendously difficult. And I obviously want you to practice so that it makes them much easier to do. Okay, so I do recommend these practice problems, and if you have any questions, please send me an email or ask them in the tutorial. Thanks, everybody.